Evaluate the integral minus 1/2 up to the square root of 2 over 4 dy divided by y square root 16y squared minus 1. So when I look at this, the first thing that I think is that I will probably have to do some sort of substitution. So I think what I'll do is I will let u be the square root of 16y squared minus 1. In other cases, I might just let it be 16y squared minus 1, but this y that we find in the denominator makes me think that I probably need to do something else. So I'm going to try this. Now, that could be written as 16y squared minus 1 raised to the 1/2 power. Then du would be 1/2 16y squared minus 1 raised to the negative 1/2 times 32y. We could simplify that to 16y over the square root of 16y squared minus 1. And of course, I forgot the dy at the end. Now, I realize that in this derivative, I have this dy over 16y squared minus 1. I've got that here also. If I were to divide both sides of this by 16y, or in other words, multiply both sides by 1 over 16y, then I'd have du over 16y equal to dy over the square root of 16y squared minus 1. So I could make that substitution. So let's ignore the limits of integration for right now, and let's just work with this integral. So dy over the square root of 16y squared minus 1, I can write as du over 16y. And I already have this other y in the denominator, so I could write that as 1 over y. Now what I would have is the integral of du over 16y squared. And of course, the problem is that I have two different variables here. So I'm going to go back and look at, well, what is 16y squared? I see it up here underneath this radical. So I'm going to work with that a little bit. So originally, we had u equal to the square root of 16y squared minus 1. So if I were to square both sides, I would have u squared equal to 16y squared minus 1. Then if I add 1 to both sides, I have u squared plus 1 equal to 16y squared. Okay, so that's looking to me like I could go back to this integral that I was working with, and I could write this as integral 1 over u squared plus 1 du. And I recognize that as the arctangent. So the arctangent of u plus c. Okay, but we're doing a definite integral here with limits of integration, so I'm probably going to find out what those limits of integration will convert to by finding u of the square root of 2 over 4, which would be the square root of 16 times the square root of 2 over 4 squared minus 1. So u of the square root of 2 over 4, then this square root of 2 over 4 squared is going to convert to 2 over 16. So I just wind up with the square root of 2 minus 1, or in other words, just 1. Or in other words, just 1. Now, u of minus a half, then, would be the square root of 16 times negative 1/2 squared minus 1. So u of negative 1/2 would be the square root of 3. So now I'm going to rewrite this original integral as the integral from the square root of 3 up to 1 dy over y square root of 1 over u squared plus 1 du, but I know that that will be the inverse tangent of u evaluated from the square root of 3 to 1. So what we have here then is the inverse tangent of 1 minus the inverse tangent of the square root of 3. The inverse tangent of 1 will be pi over 4. The inverse tangent of the square root of 3 will be pi over 3. If we get ourselves a common denominator, we would have 3 pi over 12 minus 4 pi over 12, which will be minus pi over 12.